Welcome to Science to Sleep By. Tonight, we drift into a quiet corner of the cosmos. A place where the stars hum softly in the distance, where gravity moves like a slow tide, and where even the largest celestial wanderers glide in peaceful silence. In this gentle space, we'll explore a question that sounds dramatic, yet becomes soothing when viewed through the calm lens of science. What if the interstellar object known as 3I Atlas were to collide with Earth? It's a journey through possibility, not prediction. A meditation on physics, motion, and the protective forces that surround our world. And as always, as we travel together, you are invited to relax, breathe, and allow the vastness of the universe to quiet the thoughts of the day. This is Science to Sleep By, where we explore the mysteries of the universe slowly, peacefully, and with wonder. When we talk about 3I Atlas, we're really inviting ourselves to slow down and look closely at something that has traveled farther than anything we can easily imagine. It isn't just another comet drifting inside our solar system, nor is it a leftover rock from the early days of planetary formation. Instead, 3I Atlas is an interstellar object, which means it was born beneath a completely different star, warmed by a distant sunlight we have never seen, shaped by a gravity well far from our own, and then released into the vast emptiness between solar systems. Even its name feels quiet and scientific, almost as if it echoes in a large, empty observatory at night. The 3I tells us it is the third confirmed interstellar object ever observed passing through our celestial neighborhood, following in the footsteps of 1I Oumuamua and 2I Borisov. The Atlas portion honors the Hawaii-based survey that first spotted it, using automated telescopes scanning the sky for faint and fast-moving objects. Yet even with a name that grounds it in our own scientific world, the true journey of 3I Atlas began millions or even billions of years before any human ever looked up to see it. To understand 3I Atlas, we imagine a lonely object drifting between the stars, unbound to any single solar system. Unlike most objects we know, it's not orbiting the sun. It's simply passing through, entering from deep interstellar space, turning slightly as our star's gravity tugs on it, and then continuing onward into darkness again. Many astronomers believe that interstellar objects are created when worlds form around young stars. In those early, chaotic days, planets collide, comets are thrown outward, gravitational interactions become wild and unpredictable, and rogue objects are flung into the cosmic void with enough speed to escape their home systems forever. 3I Atlas is likely one of these outcasts, a relic of planetary construction happening in another part of the galaxy, shaped by forces that played out long before humanity appeared on Earth. Each time we observe something like this, we're catching a glimpse of another solar system's history, a piece of its past drifting silently into ours. Because 3I Atlas moves so quickly and shines so faintly, observing it requires patience, sensitivity, and long nights under clear skies. Telescopes detect it not as a bold streak across the heavens, but as a faint smudge of light, slowly changing position frame by frame. To astronomers, this quiet motion is almost musical, like listening to a long, slow note that continues without interruption. For them, it becomes a reminder that the universe is constantly moving, constantly shifting, even when our world feels still. Its brightness tells us something about its surface, perhaps coated with dust from another star's nursery or darkened by cosmic radiation after ages spent drifting without warmth. Its color can hint at icy materials, frozen gases, or ancient minerals that have not changed for eons. Every data point becomes a whisper, helping us understand what this cosmic traveler might be made of. In the Science to Sleep By spirit, we can imagine 3I Atlas, not as a threat or a dramatic force tearing through space, but as a quiet, slow-moving guest entering the outskirts of our solar system. Its motion isn't chaotic or violent. It follows predictable paths shaped by gravity, the same gentle force that keeps Earth in its orbit and the moon circling above us. Even though it moves at incredible speeds compared to anything humans have built, its presence feels soft and almost serene. There is no rumbling engine, no bright flare of light, no roaring sound traveling from space to warn of its arrival. It simply glides, undisturbed, drifting through a darkness that has been its home for longer than the human mind can truly grasp. Observing such an object gives scientists a rare chance to study materials that didn't form near our sun. It's like receiving a small message from across the galaxy, a piece of physical evidence telling us that other planetary systems have gone through the same dramatic, turbulent infancy that ours once did. By studying how the surface of 3I Atlas reflects light, how it rotates, how fast it travels, and how it interacts with solar radiation, astronomers can begin to reconstruct its past. Maybe it was once part of a larger body, broken apart through a collision near its original star. Maybe it was once a comet-like object adorned with outgassing jets that slowly melted away over millions of years until it became hardened and quiet. Or perhaps it has always been small and solitary, drifting like a grain of cosmic sand across interstellar distances. For people listening at night, lying back and letting their thoughts float, the story of 3I Atlas becomes a helpful reminder of scale. This object crossed light years of emptiness, spaces so vast that even beams of light need years to travel through them before arriving near Earth's orbit. Its motion is not about intention or direction. It is simply following the leftover momentum from long ago events, carrying with it the memory of forces long gone. And when its brief visit near our sun ends, it will continue its journey outward, returning to an endless stretch of black space, untouched and unbothered by the worlds it passed. In a universe filled with stars, planets, and great luminous structures, objects like 3I Atlas show us that not everything in the cosmos is loud, fiery, or explosive. Some things travel in silence, in stillness, in patience. By understanding what 3I Atlas really is, we begin to appreciate how delicate and subtle the universe can be. We picture this tiny traveler, shaped by stellar winds and cosmic time, drifting from system to system without belonging to any of them. We follow it through our imagination as it glides beyond Neptune's orbit, past the Kuiper belt, and back into the slow quiet of interstellar space, where temperatures drop to near absolute zero and stars look like soft pinpoints scattered across an infinite night. It is here, in this stillness, that 3I Atlas has spent most of its existence, a silent wanderer, crossing the galaxy with no hurry, no destination, and no need for anything except the endless expanse before it. To understand how 3I Atlas moves through the cosmos, we have to imagine space not as an empty void, but as a vast ocean made of gravity, momentum, and gentle celestial currents. Even though we often picture outer space as stillness, the truth is that everything in it is moving constantly, drifting in paths shaped by forces we cannot see with our eyes. Stars orbit the centers of galaxies, galaxies pull on one another, planets follow predictable loops around their suns, and smaller objects, comets, asteroids, dust grains, and interstellar wanderers ride along in the gravitational tides created by all this motion. 3I Atlas is one of these wanderers, and its journey through space began long before it ever came near our sun. To picture its movement, imagine a small object being nudged by a star's gravity millions or billions of years ago. Perhaps it lived in the outer edges of another planetary system, orbiting a distant star that burned quietly in a corner of the Milky Way. Over time, gravitational interactions with larger planets or the slow shifts of nearby objects could have pushed it outward. In young planetary systems, collisions are common. Large planets scatter smaller objects, like stones skipping across water. A slight change in orbit can build over thousands of years until an object is sent drifting into the deep dark between stars. And once it escapes the influence of its parent star, it doesn't stop. It continues moving forever, carrying the momentum it gained during that ancient event. The motion of 3I Atlas is not a deliberate path. It is simply the result of inertia, the natural tendency of objects to keep moving unless something forces them to change direction. When a small body is ejected from a solar system, it can reach immense speeds, enough to travel between stars, even though the distances are staggering. Over time, its speed may change slightly as it encounters faint gravitational pulls from other stars or passes through clouds of dust. But mostly, it simply drifts along a long, smooth line through the galaxy, like a traveler walking endlessly through a quiet desert, where there is no wind and no resistance. As-3I Atlas moves through the galaxy. It crosses regions of space that vary in density, temperature, and radiation. Some areas are filled with the soft glow of starlight. Others are almost perfectly dark. It may pass near the edges of nebulae or through faint interstellar clouds that carry tiny particles left over from ancient stars. Yet even in these places, the environment is so thin and spread out that it barely affects the traveler. Space, even when not completely empty, offers almost no friction. This is why an object can maintain its speed for millions of years without slowing down. It is as though the universe is a calm, frictionless sea, letting anything that enters it move freely and endlessly. When 3I Atlas approached our solar system, it did not speed up because of any internal energy. Instead, it was pulled gently by the sun's gravity, drawn in from afar like a leaf drifting toward a quiet whirlpool. As it entered the outer regions of our solar system, the sun began to tug on it, curving its path in a graceful arc. This doesn't mean the object was trying to come to us. It simply means that gravity does what gravity always does. It reshapes motion with a steady, predictable hand. The sun's gravity affected 3I Atlas long before it became visible to our telescopes, bending its trajectory in a slow, wide sweep that changed its direction, but not its peaceful nature. To scientists observing from Earth, watching something like 3I Atlas approach the sun feels a bit like watching a feather drift toward a candle flame from across the room. The feather is not flying. It isn't falling fast. It doesn't have an engine or intention. It is simply following the invisible currents of air, the subtle forces acting on it, until its path brings it momentarily near the warm glow before carrying it away again. For interstellar visitors, that brief approach is their entire experience of the sun. They pass near it, curve around its gravitational field, and continue outward, returning to deep space, where starlight grows faint and temperatures drop once more. During its journey, 3I Atlas also rotates. Most small objects in space do. Its rotation may be slow or irregular, shaped by long-ago collisions or the subtle push of light itself. As sunlight strikes one side of the object, it can cause a tiny, gradual torque called the Yarkovsky effect. Over millions of years, even this gentle pressure can change an object's spin rate. In the vast emptiness of the galaxy, even forces as delicate as this can accumulate into meaningful changes. Astronomers study these rotations to understand what the surface might be made of. A smooth, icy surface behaves differently from a rocky one. A fragment from a destroyed planet might spin in jagged, unpredictable ways. The rotation becomes another clue, another whisper of the object's long and silent past. The path of 3I Atlas through space is shaped not only by where it has been, but by where it is going. After passing near the sun, it continues forward, curving slightly but never stopping. It follows a hyperbolic trajectory, meaning its path is open-ended. It is not bound to the sun the way planets and comets are. It will not circle back. Instead, it is like a traveler passing through a town on a long journey across a continent. Its visit is temporary, and the road ahead stretches far beyond our sight. For observers on Earth, watching something like this drift through the solar system is a reminder of how dynamic the galaxy truly is. Even though the stars seem fixed in place when we look up at the night sky, everything is always in motion. Our sun moves through the Milky Way at tremendous speed. The planets orbit the sun, moons orbit planets, and interstellar visitors like 3I Atlas glide through this complex moving system like stray messages written across the cosmic landscape. Their motion isn't a threat. It is simply a natural part of the galaxy's quiet, continuous rhythm. When we imagine 3I Atlas traveling through space, we can picture it moving with incredible patience, guided only by gravity and the momentum given to it long ago. It is a reminder that motion in the universe is constant, gentle, and enduring, shaped by laws that operate quietly across billions of miles. Looking at its path, we're reminded that the cosmos is always flowing, always shifting, always alive with movement. Even in the vast silences between the stars, to imagine an Earth collision with 3I Atlas, we have to gently step into a scenario that exists only in the realm of possibility, not prediction. It is a soft mental exploration, a quiet what if that allows us to wander through the early steps of such an event without alarm or urgency. The vastness of space makes this scenario incredibly unlikely, but imagining it can help us understand how astronomers watch the sky, how early detections work, and how cosmic motion unfolds. In this peaceful thought experiment, we explore how the earliest hints of a collision would appear, with fear, but with the calm curiosity of watching a distant storm forming over a quiet horizon dot in the beginning. The story of a potential collision doesn't start with a dramatic flash or a sudden alarm. It begins with a tiny shift in data, a faint point of light seen by a survey telescope, appearing just slightly off from where astronomers predicted it would be. Every night, automated sky surveys scan the heavens, capturing long, slow exposures of star fields. Within those exposures lie thousands of objects moving at different speeds and in different directions. Most of them follow predictable paths, shaped by the sun's gravity, but every so often, something appears that does not fit neatly into the familiar patterns. If 3I Atlas were on a path that would eventually intersect with Earth, the first clue would be an unexplained change in its position. Astronomers track objects using multiple observations spaced over hours and days. When the data points begin to trace a line that gently curves toward Earth's orbit, computer models start to calculate possible future paths. At first, these paths look like wide cones of probability, spreading out across millions of kilometers. Only with repeated measurements do these cones begin to narrow. And in our imagined scenario, each new observation would tighten the possible trajectories until one of them crossed directly through the space Earth will occupy in the future. Even in this early stage, the atmosphere among astronomers would be quiet and methodical. There would be no rush, no sudden shift in tone. Instead, the process would unfold with the same patience that characterizes all scientific work. Data would be checked, rechecked, compared with historical measurements, and sent to different observatories around the world for independent verification. Telescopes in Hawaii, Chile, Spain, and across the United States would all point toward the faint interstellar visitor, gathering as much information as possible about its speed, brightness, and direction. The news would not immediately reach the public. Scientific teams would work behind the scenes, refining the orbit to see whether the small variations in measurements were simply noise or part of a genuine trajectory that could eventually lead to a collision. At this stage, the object would still be incredibly far away, perhaps beyond the orbit of Saturn or Jupiter. Even then, its presence would be gentle and faint, a tiny speck in the wide sweep of space, no larger than a pixel on a telescope image. As more data arrives, orbital calculations become clearer. In our imaginary scenario, after weeks or months of careful observation, scientists find that the path remains steady, still pointing toward Earth. The gravitational pull of the Sun and planets could shift the trajectory slightly, but if the models continued to show an intersection point, that would be when NASA's Planetary Defense Coordination Office would quietly begin running simulations. These simulations would not be dramatic or cinematic. They would be long lines of numerical models, gentle arcs plotted across three-dimensional space, each showing a slightly different version of the object's future. Some would show a near pass, some would show a distant miss, and a small but consistent number would show a collision. This is where the human mind begins to drift into the emotional texture of such a scenario. Not panic, but stillness. The realization that something from another star, something older than civilization, could be on a path that intersects with our planet. The idea would be sobering, but also strangely calming in scale. It is a reminder of how ancient and interconnected the universe is. Something that once drifted near a distant sun could, by coincidence alone, find its way toward our world. In this imagined unfolding, Public announcements would eventually be made in the clearest, calmest language possible. NASA, along with other space agencies, would explain that a small interstellar object is being tracked and that additional measurements are underway. The tone would be steady, reassuring, focused on facts rather than fear. Astrophysicists would appear on American news networks, using simple analogies to explain orbital mechanics. They might describe Earth as a target moving through space, and 3I Atlas as a small pebble thrown from a great distance. Only if the timing and direction match precisely would a collision occur. Meanwhile, space telescopes such as Hubble or the James Webb Space Telescope might join the effort to refine the trajectory. Infrared measurements could reveal the object's size and composition more accurately. If 3I Atlas were composed of ices and dust, sunlight might cause faint jets of gas to escape, subtly altering its path. If it were mostly rock, it would remain stable. Each new measurement would further shape the potential scenario. As the object approached the inner solar system, it would grow brighter in the night sky, not dramatically, but enough for large observatories to capture clearer images. Astronomers would begin to see its shape more distinctly, perhaps an irregular fragment twisting slowly as it traveled. The data would allow scientists to model how it would behave if it approached Earth's atmosphere. Would it break apart? Would it burn up? Would it remain intact? In this imagined reality, early signs of a collision would not be loud or sudden. They would emerge as patterns in data, as curves in a graph, as slow adjustments to probability estimates. And through all of it, the universe would remain calm. Space would continue its quiet expansion. Stars would continue their fusion deep in their cores. And 3I Atlas, unaware of the attention it commands, would simply continue drifting along the ancient momentum it has carried for so long, moving at a speed it did not choose, following a path shaped only by gravity and time. If 3I Atlas were truly on a collision course with Earth, the first signs visible to humanity would not begin with the dramatic flash or a blinding streak racing across the night sky. Instead, the earliest hints would be almost unnoticeable to the average person, unfolding slowly and quietly, like a distant wind forming far beyond the horizon. The world would continue moving through its everyday rhythm, unaware at first that a traveler from another star system had set its path toward our planet. The experience would begin softly, with scientists observing faint changes long before the public ever looked upward. As weeks turn into months and the object drifts deeper into the inner solar system, astronomers would begin sharing updated measurements. These measurements, still presented calmly and cautiously, would explain that the interstellar visitor is becoming easier to track. Its brightness would increase gradually as it reflects more sunlight, emerging from the dimness of far space into a clearer portion of the sky. At this point, most people would not notice anything unusual. The night sky would still look familiar. Stars would continue to shimmer gently. The moon would wax and wane in its steady rhythm. Yet somewhere among those distant points of light, 3I Atlas would be growing ever so slightly brighter. For those with access to telescopes, the object might begin as a faint blur, almost indistinguishable from the surrounding stars. Amateur astronomers might start posting images online, noting a soft, moving dot that wasn't present a few nights earlier. Its motion would not be fast. It would not streak across the sky. Instead, it would shift slowly, its position changing only when compared with earlier star maps or long exposure photographs. Its presence would be subtle, demanding patience from those who wish to see it. Gradually, news outlets would begin to cover the story with increased interest. They would explain that the object is now bright enough to be seen through smaller telescopes, and they might even provide location guides showing where in the sky it can be found. In the United States, many people would step outside at night with curiosity, scanning the skies for this faint visitor. For many, it would feel surreal to look upward knowing that a piece of another star system is headed directly toward Earth. Yet in the stillness of the night, as crickets sing and distant traffic hums, that slow-moving speck would feel almost peaceful, a reminder of how vast and interconnected the universe truly is. As the object approaches, its brightness continues to rise. Astronomers would explain that this is not because it is heating up or glowing on its own, but simply because more sunlight is now bouncing off its surface. The interstellar traveler becomes easier to detect, not through sudden changes, but through steady, gradual illumination. Its trajectory, once an uncertain line on a computer screen, would now be well understood. Scientists would know when and where it would intersect with Earth, though they would continue refining the exact impact point with each new observation. In the months leading into the final approach, 3I Atlas would reach a brightness level where it becomes visible through binoculars. People across the United States might begin stepping outside in the quiet evening hours, holding binoculars to the sky, following online guides that help them locate the object's slow crawl across the stars. Some would describe it as a tiny point of light that seems no different from the stars around it, yet its steady motion would become apparent over long viewing sessions. As time passes, even those without binoculars might notice something faint in the sky. It would not be dramatic. There would be no fiery tail stretching across the heavens. Instead, it might appear as a slightly brighter star in a region where none existed before. Those who frequently stargaze would sense the small change. They would point it out to friends and family, explaining how it moves slightly each night, just enough to catch the attention of a patient observer. The world would experience a strange blend of awe and quiet contemplation. For many, the idea that something from beyond our solar system is approaching Earth would spark an introspective curiosity. It would remind people of how small our world is in the grand structure of the galaxy. It would remind them that even in this vastness, rare events unfold that connect distant star systems to our own. The sky would become a place of reflection, a canvas where cosmic history is painted in slow, deliberate strokes. As the object continues to draw nearer, it eventually reaches a point where it becomes visible to the naked eye. Not bright, not glowing with the intensity of a fireball, but appearing instead as a new point of light that seems slightly different from the others. It might shimmer in a way that feels unfamiliar, or move just enough from night to night that attentive observers begin sharing their experiences online. Families in American suburbs and countryside towns would stand outside, pointing upward, witnessing the slow approach together. NASA and other agencies would release clear explanations, reminding the public that although the object is approaching, its brightness does not necessarily indicate danger in itself. They would explain the physics of reflectivity, momentum, and gravitational paths. Their tone would remain steady and educational, offering reassurance while guiding people's understanding of the cosmic event unfolding above. As the object reaches its final weeks of approach, humanity would collectively experience something that rarely happens: a worldwide awareness of a single object drifting toward our planet. Across the United States, people might gather in parks, rooftops, and open fields to watch the deepening glow in the night sky. Even though the thought of a collision carries heavy implications, the visual experience would still be serene. The object would drift closer, its light growing not explosively, but gradually, like a new star rising with each passing night. Through clouds of uncertainty and the gentle unfolding of cosmic motion, 3I Atlas would become one of the few interstellar visitors ever observed by human eyes. Its presence transforming the sky into a quiet reminder of the universe's vast scale and ancient history, all unfolding above a world watching in silence and wonder in the quiet hours before dawn, long before most of the world wakes. The first true physical signs of 3I Atlas entering Earth's atmosphere would begin to unfold. This moment, the atmospheric entry, represents the final stage in a journey that has lasted millions of years. For so long, this interstellar traveler has drifted freely through the Milky Way, untouched by atmospheres, untouched by friction, untouched by anything except the gentle pull of distant stars and planets. But now, for the first time since it was cast out of its original star system, it encounters resistance. Not a violent clash at first, but a soft whisper of molecules brushing against its surface, signaling the beginning of a transformation shaped by heat, drag, and the unyielding laws of physics. Even before the object becomes visible in a dramatic way, its interaction with the upper atmosphere would create subtle changes. High above the Earth, where the air is thinner than any vacuum chamber humans could build, tiny molecules begin to accumulate in front of the object as it plunges forward at incredible speed. These molecules cannot move out of the way quickly enough, so they compress. When air compresses, it heats. This heating is what causes meteors to glow, not friction as many assume, but the intense thermal energy created by compressed air being forced aside at tremendous velocities. For a visitor like 3I Atlas, traveling possibly tens of kilometers per second, this compression becomes extreme. As it descends deeper into the atmosphere, the heating intensifies. The object's surface, once icy cold from eons in interstellar space, now encounters temperatures hotter than the surface of the sun. The glow would begin faintly, a soft pulse of light in the upper sky, barely noticeable to anyone not already staring upward at the correct moment. Because much of this process begins at altitudes far above where commercial aircraft fly, the earliest stages may go unseen by human eyes. Yet the transformation has begun, and the once dark traveler now carries a soft envelope of ionized gas, plasma created by the superheated air around it. If 3I Atlas were composed of fragile material, icy, dusty, or porous, it might begin breaking apart at this stage. Interstellar objects are often unpredictable in structure, shaped not by a single history, but by collisions, radiation exposure, and cosmic aging. Some are loose aggregates of dust and rock, held together only by weak gravitational bonds. If 3I Atlas were such an object, pieces might begin shedding off, forming a trailing stream of glowing fragments that burn brightly as they separate. These fragments would create streaks across the sky, like multiple meteors traveling together. The overall appearance would be reminiscent of a slow, expanding firework, drifting downward in graceful arcs through the atmosphere. If the object were instead solid and dense, made of rock, metal, or compacted minerals, it would remain intact longer. Its descent would produce a single, bright fireball that grows steadily more radiant as it moves deeper into the thickening air. People on the ground, particularly in areas beneath the projected impact zone within the United States, might begin noticing a strange glow in the sky. It would not resemble a typical shooting star, which lasts only a fraction of a second. Instead, this would be a sustained, slow-moving light, growing brighter with each passing moment. Some might describe it as a burning ember drifting gracefully across the heavens. Others might recall seeing Ray entering spacecraft, though this object would appear far brighter and move more directly downward. For those observing from a distance, the descent would be almost hypnotic. The interstellar visitor would cast a gentle radiance across clouds, illuminating the early morning or late evening sky with shades of orange, white, or even blue, depending on its composition and velocity. The ionized air around it would shimmer with energy, creating the appearance of a glowing halo. In some cases, atmospheric ions can produce soft, ghostly colors, not unlike the aurora borealis, though much more brief. This would create a unique visual event, one of those rare cosmic moments that blend beauty with profound, humbling scale. As the descent continues, the sound would begin to catch up with the light. Because the object is traveling so fast, observers on the ground would see the glow long before they heard anything. Then, moments or even minutes later, a distant rumble might drift through the air. At first, it may resemble thunder from a far-off storm. The sound would be soft, rolling, and delayed, caused by the shockwave produced high in the atmosphere. These shockwaves ripple outward in expanding circles, eventually reaching towns, forests, and cities below, creating a low, resonant vibration that people feel in their chests more than they hear with their ears. If the entry angle were shallow, the object might skip once on the upper atmosphere, similar to a stone skipping off a pond. This would cause dramatic flares of light as energy is released in bursts, but the object might continue traveling until gravity finally pulls it back into a steeper descent. If the angle were steep, it would plunge more directly toward the surface, losing speed rapidly as the dense lower atmosphere exerts immense drag. In either case, the brightness would reach a peak where the entire sky might momentarily seem illuminated, even in pre-dawn hours. Shadows would stretch across the ground. Animals might stir, confused by the sudden flash. Night would briefly give way to light. The final moments of atmospheric entry would determine the nature of the impact. If the object remains intact until the lower atmosphere, it may reach the surface as a single, powerful body. But if it breaks apart earlier, a shower of fragments could create multiple smaller impacts spread across a wide area. Each scenario carries different implications, but visually and physically, the descent would be equally extraordinary. In this imagined moment, 3I Atlas is experiencing a transformation unlike anything in its long history. After millions of years drifting silently through cold interstellar space, after passing distant stars and crossing dark cosmic voids, its journey meets resistance for the first time. The atmosphere becomes both sculptor and storyteller, shaping the object's final path and revealing it to the world in a brilliant display of light, heat, and motion. And through this transformation, humanity watches the sky with a mixture of awe, uncertainty, and profound recognition of the vast forces that govern our universe, the quiet aftermath of an interstellar object making contact with Earth. The planet enters a period of profound yet gradually unfolding transformation, a slow reshaping that begins not with violent motion, but with the settling breath of a world-absorbing shock. When scientists contemplate the global effects of an impact, they describe a chain of events that moves outward in waves, airborne particles rising toward the sky, temperature patterns shifting with patience, oceans responding with deep and ancient rhythms. In the calm light of this imagining, we can explore the delicacy and complexity of Earth's reaction, recognizing that even in the face of disturbances, the planet follows its own measured rules of physics and climate behavior, reacting in ways that stretch across weeks, months, and years rather than minutes. The world does not change all at once. Instead, it transitions in a drifting, gradual manner, almost like a long exhale after a sudden inhale, allowing the atmosphere and surface to adjust piece by piece. One of the most immediate effects following an impact of a deep space object is the lofting of fine particles into the upper atmosphere. Dust, ash, and vaporized material may rise high enough to reach the stratosphere, a region where winds move differently, and where tiny particles can linger for long stretches of time. In this thin, delicate band of air, the particles behave almost like a soft veil drawn across the sky, scattering sunlight in ways that can subtly dim the brightness of the day. Scientists call this phenomenon radiative forcing, but in simple terms, it is like placing a thin filter over the sun, allowing light to pass through but reducing its warmth. The effect is gentle at first, barely noticeable, yet over time, it shapes climate patterns in ways that flow outward across continents. As sunlight becomes slightly reduced, temperatures at Earth's surface begin to shift gradually. The cooling does not sweep across the planet like a sudden winter storm. Instead, it drifts in softly, affecting some regions more than others, depending on atmospheric circulation. Areas near the equator, where sunlight is most direct, might experience the changes more slowly, while higher latitudes already accustomed to colder conditions may feel the cooling more distinctly. These alterations can influence jet streams, the high-altitude rivers of air that define storm paths and seasonal weather. A shift in temperature gradients changes these jet streams in subtle arcs, bending their usual flow and redistributing rainfall. Some regions may find themselves experiencing quieter skies and reduced precipitation, while others may notice storms taking unfamiliar routes, wandering slightly farther north or south as the atmosphere settles into its new balance. The oceans respond with their own form of patience, for they hold both heat and cold with immense persistence. When the surface cools, the upper layers of the ocean adjust slowly, like a vast reservoir, shifting its temperature by fractions of a degree across enormous distances. The mixing of warm and cool water can influence major currents, including the great conveyor belts that circle the planet's seas. These currents, such as the Gulf Stream in the Atlantic, carry warmth to northern climates, maintaining mildness in regions that would otherwise be far colder. Even slight changes in atmospheric temperature can lead to shifts in these currents, altering the distribution of heat through the oceans in ways that modify regional climates over long timescales. This does not happen suddenly. The oceans move with their own rhythm, responding to surface changes through slow, layered mixing, creating a gentle cascade of effects that ripple through marine ecosystems. Marine life itself feels these changes in the gradual adjustments of temperature and sunlight penetration. Cooler surface waters may promote nutrient upwelling in some regions, supporting blooms of microscopic organisms that feed entire food chains. In other places, the reduced sunlight may diminish photosynthesis in surface waters, affecting the delicate balance of marine ecosystems that depend on stable conditions. Coral reefs, sensitive to even small environmental changes, may enter periods of stress, while deep-sea environments, insulated from surface events, continue their ancient rhythms largely undisturbed. The oceans become quiet participants in the planet's recovery, shifting gently in response to the new atmospheric conditions. As global temperatures change, the winds at the planet's surface also evolve. Winds are born from differences in pressure and temperature, and when cooling occurs on a planetary scale, these gradients adjust slowly. The result is a shifting pattern of breezes and storm systems that take new paths across continents. Regions that once experienced predictable seasonal winds may notice those patterns stretching, softening, or arriving slightly earlier or later than before. These changes, though mild at first, gradually redefine climate zones, creating environments that encourage certain plants and discourage others. Forests may experience slower growth. Grasslands may spread or retreat depending on moisture availability and temperature gradients. Nature adjusts quietly, moving with the rhythm of Earth's evolving conditions. The long-term climate effects depend heavily on how much material reached the upper atmosphere and how long it remains suspended. Over time, rainfall helps to bring these particles back to the surface, washing the atmosphere clean and gradually restoring clarity to the skies. As sunlight returns to normal strength, temperatures rise again, allowing the climate to begin stabilizing. In this slow return to equilibrium, the planet demonstrates its resilience, shifting from altered conditions toward a familiar balance. Ecosystems respond in their own time, regrowing, migrating, or adapting as the environment settles into a new and stable pattern shaped by the changes that unfolded after the impact. Throughout this entire process, the world continues its natural cycles, orbiting the sun, tilting through seasons, and rotating beneath shifting skies. Even after an event that introduces dust and cooling, Earth systems remain dynamic and self-correcting, guided by the same physical laws that have governed the planet for billions of years. The atmosphere, oceans, land, and life interact in a harmonic balance that slowly reasserts itself as the dust settles and temperatures drift back toward their long-term averages. While the changes following an impact may reshape the climate temporarily, the planet steadily moves toward recovery, demonstrating its remarkable capacity to absorb disturbances and continue its quiet journey through space. In the moments after scientists confirm that an interstellar object like 3I Atlas is on a collision path with Earth, the world enters a phase defined not by panic, but by coordination, decision-making, and a profound sense of shared purpose. Across continents, communication networks activate, research institutions begin exchanging data, and the intricate machinery of human response starts turning with quiet urgency. In the United States, agencies such as NASA, FEMA, NOAA, and the U.S. Space Force would immediately shift into synchronized motion, drawing upon years of planning, simulations, and preparedness exercises designed for precisely such improbable but significant cosmic events. Although the scenario might feel unprecedented, humanity is far from unprepared. In truth, the foundations of resilience have been laid through decades of scientific advancement and cooperative strategy. As the impact approaches, the response becomes a testament to humanity's ability to organize and adapt, revealing strengths often hidden beneath the routine patterns of daily life. NASA's first responsibility would be to refine the object's trajectory with absolute precision. Using data from ground-based telescopes, space observatories, and radar networks, they would map 3I Atlas's motion down to the smallest realistic margin of error. At the Jet Propulsion Laboratory in California, mission planners and orbital analysts would work around the clock, calculating possible outcomes and identifying any opportunities for intervention. If there were enough time, discussions would surface around launching a deflection mission, an effort to alter the object's course using spacecraft. The United States has already demonstrated the feasibility of such missions through kinetic impact experiments like the DART test, which showcase the ability to nudge an asteroid off its path. Although 3I Atlas is interstellar and significantly faster than typical solar system objects, the existence of these technologies underscores humanity's determination to protect its home planet whenever possible. Even if intervention proves impossible due to timing or object characteristics, the collaborative drive to understand and prepare would continue with unwavering dedication, while NASA refines data and informs global partners. Federal and state emergency management agencies begin preparing for the possible effects on specific regions. Large meetings take place quietly across the country where leaders consider everything from population relocation strategies to infrastructure resilience. The tone of these preparations is methodical, measured, and grounded in decades of disaster management experience. FEMA, with its vast network of logistical support, coordinates with governors, state emergency operations centers, and local communities to ensure that evacuation routes, shelters, medical facilities, and food distribution networks are ready to handle sudden displacement if needed. Military bases across the U.S. stand by to provide transport, medical support, and engineering expertise. These actions unfold not with dramatic urgency, but with the calm precision that emerges when systems built for protection begin functioning exactly as intended. The scientific community plays an essential role in shaping public understanding during such a moment. Researchers across the United States contribute to models that simulate atmospheric impact, energy release, seismic effects, and potential recovery timelines. Universities from coast to coast become hubs of analysis and communication, where experts in geology, climatology, astronomy, and environmental science collaborate through shared databases and virtual conferences. Their findings help guide policymakers and emergency planners, ensuring that the response reflects the best available science. By measuring the polarization and wavelength of that light, researchers can deduce the texture of its surface, the composition of its dust, and the density of its coma. Radio telescopes can probe for molecular emissions like hydroxyl or cyanide radicals, providing chemical fingerprints of its volatile materials. Meanwhile, the James Webb Space Telescope, observing in infrared, can detect subtle heat signatures and track how sunlight penetrates the dusty envelope, revealing clues about its internal structure. All of this data will help astronomers build an unprecedented three-dimensional model of an interstellar visitor, transforming theory into tangible understanding. Public anticipation mirrors the scientific excitement. Just as the world once watched the first images from the Rosetta mission or the dramatic close-up of Pluto by New Horizons, people now look to the sky with curiosity and wonder at 3I Atlas. Documentaries, digital simulations, and educational programs are already being developed to help audiences grasp the magnitude of this event. It's more than just a comet, it's a bridge between star systems, a cosmic enver crossing the void. For many, it symbolizes the unity of exploration and the boundless curiosity that defines the human spirit. Amid the excitement, scientists remain aware of the fleeting nature of such opportunities. Interstellar objects like 3I Atlas spend only a short time within the reach of our instruments. The window for observation is measured in months, not years. Once it passes the sun and slingshots back into interstellar space, it may never return. Every telescope pointed at it, every experiment planned, and every image captured represents a race against time. That awareness fuels a quiet intensity among astronomers who know that moments like this define generations of discovery. The anticipation surrounding 3I Atlas, therefore, is more than just academic. It's emotional, philosophical, and deeply human. It represents the rare intersection of preparation and chance, where the machinery of science meets the unpredictability of the cosmos. For every scientist poring over data or sketching mission trajectories, there is a sense of standing at the edge of something historic, a reminder that, in the vast expanse of space, we are not isolated observers, but participants in an unfolding cosmic dialogue carried by dust, ice, and starlight. Revelation that 3I Atlas is on a trajectory bringing it closer to Earth than any known interstellar object before has ignited a complex mixture of fascination, urgency, and reflection among scientists, policymakers, and the general public. For the scientific community, this is not a story of danger, but of opportunity, an unprecedented chance to study an alien visitor within our cosmic neighborhood. Yet, the implications of its passage are profound, extending far beyond the boundaries of astronomy. It challenges how humanity perceives its place in the universe, rekindles discussions about interstellar exploration, and opens new pathways for global scientific cooperation. The potential impact of 3I Atlas reaches across disciplines from planetary science and chemistry to philosophy and cultural understanding, marking it is one of the most significant celestial events of the century. When astronomers first calculated its trajectory, one of the earliest public concerns was whether 3I Atlas posed any physical risk to Earth. The answer, grounded firmly in observation and orbital mechanics, is no. Its path, though passing through the inner solar system, will remain at a safe distance far enough that there is no possibility of collision. But the very fact that it will come close enough to be observed in detail offers something even more valuable: a front-row seat to interstellar science in action. For months, observatories will track its brightness, shape, and composition, while instruments in orbit will collect data about the gases and particles it releases as it nears the Sun. The proximity allows for a resolution never before achieved with such an object, transforming what would normally be a distant mystery into a near-field laboratory. For scientists, this represents a rare convergence of timing and technology. With telescopes like the James Webb Space Telescope operating in infrared, the Vera C. Rubin Observatory preparing to map the sky in unprecedented detail, and upcoming missions like NASA's Comet Interceptor ready to respond to transient cosmic visitors, 3I Atlas arrives at a moment when humanity is most capable of studying it. The object's visit serves as a proving ground for rapid coordination science, where data from multiple platforms, space-based, ground-based, and even airborne, can be combined in real time. This model of scientific agility is likely to shape how future astronomical phenomena are approached. Whether they be comets, asteroids, or even distant exoplanetary transits, the broader impact on planetary science is immense. Every sample of dust or spectral signature captured from 3I Atlas could reveal how other solar systems form and evolve. Understanding its isotopic ratios and molecular composition allows scientists to compare its chemistry to that of comets native to our own system. If 3I Atlas exhibits different proportions of water, carbon monoxide, or organics, it may indicate that planetary formation processes vary widely across the galaxy. This could challenge existing models of how habitable environments arise, influencing how future telescopes search for life around other stars. If the building blocks of life are found to be common across systems, it strengthens the argument that life itself may be a galactic phenomenon rather than a local anomaly. Beyond chemistry and composition, 3I Atlas's arrival also impacts the physics of how interstellar objects move. Studying its orbit and the subtle effects of solar radiation, pressure, outgassing, and gravitational perturbations will refine our understanding of interstellar dynamics. The more precisely scientists can measure its motion, the better they can predict how such objects are ejected from their home systems and how often they pass through ours. This has direct implications for the detection of future interstellar bodies. Astronomers estimate that thousands of such objects may be drifting invisibly through our solar system at any given time. The insights gained from tracking 3I Atlas could help refine search algorithms and sensor designs. ensuring that the next interstellar visitor does not go unnoticed until it is long gone. The potential for public engagement is equally significant. Few astronomical events capture global attention like a celestial visitor visible to the naked eye. As 3i Atlas brightens, it may become a spectacle in the night sky, a glowing thread among the stars that invites wonder and curiosity. For educators, it presents a perfect moment to connect the public to science, to explain not just what this object is, but why it matters. Museums, observatories, and science communicators across the world are already preparing exhibits and broadcasts to help audiences experience the event. It's an opportunity to remind people that the universe is not distant or static. It is alive, dynamic, and filled with travelers from other suns. Within the scientific community, the collaborative nature of 3i Atlas's study represents a milestone in how knowledge is shared. Data collected by one observatory is being distributed globally within hours, enabling real-time analysis and interpretation. Artificial intelligence systems are assisting astronomers by processing terabytes of imagery, identifying patterns that human eyes might miss. This level of integration across nations, institutions, and even machine-human partnerships marks a turning point in scientific methodology. The study of 3i Atlas may well become a model for future research on transient astronomical phenomena, demonstrating how agility, openness, and collaboration can lead to deeper insights. Philosophically, the arrival of an interstellar object so close to Earth invites reflection on humanity's connection to the greater cosmos. For centuries, humans have looked to the stars and wondered whether other worlds exist, whether life elsewhere shares our chemistry, and whether the universe itself follows universal patterns of creation. 3i Atlas provides a tangible reminder that the boundaries between star systems are not impassable. Matter travels between them, carrying with it the history of alien suns and the dust of long-lost planets. In that sense, our solar system is not isolated, but part of a grand, interconnected galactic ecosystem. The particles that make up 3i Atlas may one day become part of another world, just as some of our own cometary material may already be drifting among distant stars. For researchers in astrobiology, this event carries a deep scientific resonance. Interstellar objects like 3i Atlas might act as natural couriers, spreading organic compounds and prebiotic molecules across the galaxy. As we bring this journey to a close, we return to the quiet, reflective tone that has guided every part of this exploration. Imagining what might happen if an interstellar visitor like 3i Atlas collided with Earth allowed us to step into a world of scientific curiosity, slow-motion reasoning, and gentle cosmic awareness. From the faint first detection in the darkness of space, to the unfolding chain of physical events, to the global responses shaped by preparation and resilience. Each step revealed not chaos, but a steady rhythm governed by the laws of nature. This scenario, though dramatic in thought, transformed into a soft meditation on how planetary systems behave, how humanity organizes in the face of uncertainty, and how the universe operates with a balance so much larger than our fears. We explored the nature of interstellar objects drifting between the stars, understanding their lonely journeys and the incredibly small chance that their paths would ever intersect with Earth's orbit. We examined the physics of atmospheric entry, the cascading effects of shockwaves and global cooling, and the quiet, patient recovery of Earth's climate, oceans, and ecosystems. In the midst of these scientific ideas, we watched how the United States and the larger world would respond, not with panic, but with coordination, clarity, and the mindset born from decades of scientific planning. Humanity's resilience emerged not from strength alone, but from cooperation, knowledge, and the instinct to protect one another. Yet the most reassuring truth came from the cosmos itself. The universe, vast beyond comprehension, creates natural protections through distance, scale, and gravity. The likelihood of a true interstellar impact is so small that it almost dissolves into nothingness, reminding us that Earth is not as vulnerable as our imaginations sometimes suggest. The solar system's architecture, the predictable paths of planets, and the influence of massive celestial bodies all work together like a quiet shield, guiding visitors like 3i Atlas into harmless trajectories. Through this entire script, we saw how science can soothe rather than alarm, offering explanations that calm the mind while expanding our sense of wonder. It invites us to look upward, not with fear, but with curiosity, understanding that the universe does not lean toward catastrophe, but toward stability across immense spans of time. These reflections reveal not the fragility of Earth, but its remarkable ability to endure, adapt, and remain stable within a cosmic environment that is far more peaceful than it first appears. And so, as we conclude this exploration, we find comfort in both our scientific preparedness and the natural safeguards built into the universe itself. Earth continues its steady orbit, oceans continue their ancient cycles, and the stars maintain their distant watch, allowing us to rest with the knowledge that while imagining these scenarios expands our understanding, the reality of our world remains secure, resilient, and guided by the predictable harmony of the cosmos.